So welcome back. Today is Monday, 30 October. This is CSC241 Computer Architecture. What I'd like to do is call your attention to a quick assignment we're going to review shortly. It's assignment 4.2, and it'll be due by the time we start class on Friday at 10 a.m. Once again, we do not have class on Wednesday. It is Liberty Day and the campus is closed. So if you're in CSC 241, we will not plan to have a class or meet on Wednesday. And I hope you enjoy the celebration and return to us in good health on Friday. So without further ado, one of the things that we wanted to do when we were talking about digital devices and the richness of those digital devices is to call out how the physical digital devices are represented to software through the operating system. So one of the important things about the components that make up a full-scale computer is this idea that software applications for general purpose computing exist for a variety of purposes, right? And for all sorts of people. So the charm about general computing capabilities with hardware or complex language, and this is something we'll learn in our next module. There are different flavors or styles of CPU. The CISC processors, complex instruction set processors, are designed explicitly for all sorts of purposes, general applications. So you might ask yourself, if I have, and I'll go ahead and open up File Explorer, if I have a computer and it's made of a variety of digital components, and I go to the Manage option here, I can open up a utility called Device Manager. Does everybody see Device Manager here on the screen?
Yeah.
All right, so Device Manager, well, computer management. So we select in File Manager, we select the computer name where it says this computer or my computer, and we right-click that and we go to Show More Options and select Computer Management. Inside the Computer Management console is an option called Device Manager, and you can actually find this if you go to Control Panel and then open up Advanced or Administrative Tools in Windows 10. There's something called Administrative Tools. In Windows 11, Control Panel shows the same thing under Windows Tools. And once you're inside there, you'll see something about Device Manager, right? So it has to do with devices. Inside Device Manager, if you expand, it'll show all of the different digital components for that computer. And I've named my computer after a character in a sci-fi film. But basically, you'll see all of these different digital devices. And this is one task of the operating system. So hardware is the physical, and then software is closest to the user, and in between is the operating system. And you might ask, how is it that 15 different applications can each make use of my display adapter so that I have independent context windows for every one of those 15 applications? If I have a web browser open with 16 different tabs, and then I have a PDF reader, and I have some graphics I'm showing, how is it that all of these different applications can play nice with each other when there's only one display adapter? And that's the role of the operating system. The operating system takes all of the different types of digital devices. So in the world of computing, unless you're working with Apple computers, and we'll talk about Apple computers separately in just a moment, most personal computers are created by a variety of companies. So you have different brands, different models, different features of the display adapters, right? The actual screen itself, the actual monitors they're connected to, right? The CPUs, the memory chips, the network cards, all of these are different. And if you're creating software to work on all of those different types of computers, if you weren't careful and you didn't know any better, you'd have to create code that would play nice with all of those different models and brands. In simple terms, computer scientists would never have a chance to live. They would be constantly rewriting and recompiling code to the extent that every time a new brand and a new device came out, they'd have to be at work, working overtime to rewrite the algorithms and recompile the algorithms. And so they'd never have dates. They'd never enjoy a social life. They would never get married and procreate. They wouldn't have children. Computer scientists would be extinct right now. And I know that I'm kind of stretching the reality of things right now, but the truth is, if you look at all the brands and all the models and all the different types of devices, it's kind of a no small miracle sort of situation that software created for a single purpose could run on 57 different types of brands and models, right? Actually, hundreds. Are there any comments or observations? Now, we have separate classes where we deep dive into the operating system, right? So we explore operating systems in much greater depth. But the thing that I want you to be impressed with today is where RAM comes in. So random access memory is used by the operating system with the physical device. So the physical network device here, the operating system interacts with the actual physical hardware through something called a device driver. And it creates a virtual representation of that Wi-Fi adapter. So my laptop has an Intel-based Wi-Fi 6 adapter, and the model is explicitly an AX201. Does everybody see that? It's not an N or a G capable Wi-Fi card. It's not even an AC capable Wi-Fi card. It's an AX capable Wi-Fi card. So it's pretty state of the art, right? And my question is, how do all the web browsers in the world know how to work with this? How is that even possible, right? How is that even possible? And the answer is the operating system. So you have hardware devices on the physical level, on the most basic level, and then you have application software, all these different kinds of applications that have to run, even though the brands and models are all different. And the operating system creates a virtual representation of that physical hard drive or physical, see, there's a physical hard drive, right? A Western Digital green, a Western Digital black, a virtual representation of my keyboard, a virtual representation of my mouse, a virtual representation of the web camera and the Bluetooth, right? What else? The USB ports, the processors. Okay, so we have universal serial buses, we have USB ports, we have Ethernet ports, we have video connectors, right? We have sound. So we have sound devices that work the magic when we're gaming or we're just watching a YouTube. We have all of these different devices, and the operating system takes the actual physical device driver and it creates a virtual representation of the real thing in memory. And if you right-click your Wi-Fi adapter, you'll notice that when you go in here on the screen and look at something called resources, here's the memory range that's used. Here's the random access memory range that's used to build out the virtual representation of that physical device. Okay. Now that's significant because when your applications are communicating through the Wi-Fi to the internet, and all of these different applications are using and sending and receiving data, something we take for granted all the time, they're not interacting directly with the hardware. They're not doing that. They're interacting instead with a virtual representation of the device, and the operating system creates a virtual copy of every single physical device on that system so that every piece of software can take up a spot of its own in that memory range. So to answer the question, there's enough address memory for multiple Wi-Fi cards. Every application has its own Wi-Fi card. It has its own version of the Wi-Fi card, and every application works with its own virtual representation of the physical Wi-Fi card. And that's because there's ample memory space available or set aside or reserved for that specific physical device, right? The virtual representation of that physical device. What I want you to do for your assignment is I want you to walk through the same steps you've just seen me do, where you open up File Manager, you find my computer or this computer, you right-click it, you go to Show More Options or to Manage, right? And then when you open this up, you're in computer management mode, so you're going to select the device manager, and you'll go to the network adapters specifically. You'll find your Wi-Fi card because that's the one that's active right now. And then you'll right-click it with the right mouse button and select Properties, go to the Resources tab, and capture a screenshot of this and upload it. Now I'm going to see a different version of the Wi-Fi. If I see Intel Wi-Fi 6 AX201 and I see the exact same memory range, I'll know you're a copycat. And that's actually happened before. So don't do that, okay? But go ahead and do it yourself. Hit the print screen button after after you've gotten to this point, right? While that's showing, hit the print screen button and paste it into a Word document or into Paint. And then save it as a JPEG. So once again, I'm going to show the properties, and I'm going to hit my print screen, and then I'm going to paste this in here and save it as a JPEG image file. And I'll call this in here under assignments in module 2, we'll call this T-Kentop Device Manager, or T-Kentop 4.2 assignment, right? Everybody got me? And then you submit it, and then you're done. And that's all you're doing here. So you're gonna go ahead and capture on your own system, just like we showed you here in the Resources tab. The memory address range must be clearly shown for credit. Now, why do I say the memory address range must be clearly shown for credit? you can find that in some cases, because of the way the device driver works, it's actually part of a different component. So not every single, let me pull this back here. Can everybody see my screen?
Yeah, I see it.
Everybody can still see my screen? Okay. Oh, nuts. I guess I had two of them showing. I'm not sure why closing one would close them both, but when you select some of these, depending on what it is, there may or may not be RAM, there may not be a resources tab. So in some cases, the virtual representation of a physical digital component is brokered through another device. For example, in the case of a hard disk, there could be a disk controller that's down here in the system devices. And that's often the case. Hard disks are connected to the motherboard physically by a hard disk controller. And if you go inside the storage controllers option, then you could find where those connections are staged or provisioned, and that's how they're built, right? So you're going to find that some of these devices don't always have a memory allocation and a resources tab. They don't always have that, but there are other components that do. The safe bet is to pick the network device, right? This always works, it never disappoints. Find the Wi-Fi adapter and go to properties. That's why I recommend doing that. Now, if you can find other devices on your system that include address ranges in the properties under resources, and you include that, I'll post additional credit. But everybody's system is different, and it all depends on the architecture that's built into the motherboard, the chipset, and so on, right? So you have these other system components on the motherboard that broker the memory address range. I just want you to be aware of that. So it's not an absolute thing for every device that's listed, but ultimately, in order for the operating system to work with a physical digital device, you have to have a memory address range in RAM somewhere, or there's no way for applications to use it reliably. That's how we allow applications to play nice with each other. Are there any questions about this particular assignment and what we just related here out of your study guide?
Yeah, for me. So can this be done on the Mac, or should I just use the virtual machine and submit that screenshot?
You can use the virtual machine. That's a great question. So
All
on
right.
the Mac, you could just open the virtual machine and then do it in the virtual machine. Okay?
Yeah.
Okay. Now, for our last topic today, and this is the end of our study guide, we want to talk about the computational magic. We want to swing back and refocus on the processor and how the processor depends on sequence and logic gates. And we want to take a moment just to share an homage of what things were like before calculators existed, before CPUs, before arithmetic logic units were invented, and how some folks made a living by being the human version of a CPU, okay? So the most important, I think one of the most important developments of computer architecture and digital physical components is this idea of timing and sequence. And we've talked about that. We said that there's some magic that happens when you have a system clock and you can order the execution of specific statements as intended, right? Otherwise, everything just happens all at once. You don't have the means to control a specific sequence. And without that capacity, things just don't work right. The whole notion of sequence comes from a timing mechanism. So one of the most important and underappreciated digital components in a computer system, can everybody see my screen?
Yes.
Is the function of a system clock. And a system clock can be a crystal. It can be a mineral crystal that vibrates or oscillates when a current is passed through it. So if you pass electricity through it, then basically there's activity, right? And it vibrates. And there are other components, digital components, that function like that, and actually electricity itself, right? There's 60 cycles in our alternating current, there's 60 cycles, but we both know that computers don't operate on 60 rounds a second or 60 pieces of computation each second. Computers are much, much faster. So the cycle that is created by the electronics happens at a much faster rate than the cycles that we see in alternating current from our electrical outlets. The timing happens 1,000 times a second, that's kilohertz, or 1,000,000 times a second, that's megahertz, or 1,000,000,000 times a second, that's gigahertz. And the thing that I want you to understand is that there's kind of a natural rhythm and progression to the way that the clock operates. And a cycle is defined as a measure between the peak to the peak or the trough to the trough. So what you have is a sine wave here, right? And without getting too mathematical, one thing we want you to understand is that these sine waves can occur at different rates. So as we said, they can be 1 billion times a second, 1 billion waves per second, or it can be 1,000,000 waves per second, or 1,000 waves per second, giga, mega, and kilo, respectively. The important thing to understand is this term hertz. So a cycle is one tick or increment of the clock. And if you get 1,000 of those, 1,000,000 of those, or 1 billion of those every second, what's happening is that every time you get a peak and these waves are moving past a single point, the wavelength is defined as the distance between the peaks or the distance between the troughs. That's what we would call wavelength. And in terms of what's a tick or a talk or a cycle, that's also from a trough to a trough or a peak to a peak, because as you travel from peak to peak, your oscillation starts from the highest point and runs down to the lowest point and then back up to the highest point. It's kind of like the hands of a clock that start at 12 o'clock and work all the way around the dial and then come back where? To the very beginning at the top. So this is just a graphic representation of what's going on there. But the thing to understand is what happens with the system clock. It generates a series of cycles at different rates depending on the nature of the electronic device. And for computers, that's very, very fast. And this natural rhythm is what allows our CPU to control things in a sequence. Any questions about what we've shared here? So this link, I just want to make sure the link is working right. We need you to watch this. So there's more information about how flip-flops work. And by the time you watch this, some of these other concepts will start to click. And Wait a minute. There's also, so when you have computers that are taking on a complex series of mathematical and Boolean operations, when you're doing things one after another in a series, that's what we mean by sequence. It's the sequence that's actually doing it, right? So back in the day, human beings had slide rules, and then they had calculators, and they performed mathematical calculations in a sequence. Now, believe it or not, before we actually had calculators or computers, how many of you have heard of the movie called Hidden Figures? Anybody?
No.
Yes, I watched it back in I think it was
Yeah.
middle school.
So this is actually a true story, based on a true story. And it's very inspiring because, you know, there were young female professionals who were at the top of their game in mathematics. And it turns out that they were very much unappreciated. But NASA had a problem. They could not calculate the mathematical computations to safely launch the first manned rockets into space, right? So when NASA first put humans into space and started working with rockets that left our Earth's atmosphere and went into orbit, they didn't have the computational capacities to do this. And so this was done by hand, and in many cases by slide rule, because again, calculators didn't exist. Graphing calculators didn't exist. And graphing calculators were basically the first primitive computer. So when you think about how computers have evolved, everything that goes into a graphing calculator is technically a specialized computer, and that's what it does. So we mentioned before that Texas Instruments and Hewlett-Packard were two of the leading companies to provide that kind of capacity. Had NASA access to those graphing calculators, then this scenario would have never played out. And one of the things that we fail to appreciate in everyday life is how our industry has stood on the shoulder of giants, and how there were innovators who did amazing things with math and in science, and this eventually led to the accelerated development of computing capacity, right? So everybody started to realize that this kind of ability was a precious commodity, and that we needed to put more resources like this in the hands of more scientists and engineers to solve the world's problems. And so our NASA space program was kind of an accelerated offshoot of the arms race between our country and Russia, the other superpower in the world. And so this led to more aggressive development of computing and the first computers. But I just thought that it was important to share some of the origins of how and what we do with computers. So when you think about it, if they were able to help NASA solve their problems, what would happen if they had access to a supercomputer? And the truth is, when you understand how computers are built out of the digital components, and then you understand what kind of resource you really have at your fingertips, you begin to appreciate how it can be used to solve all kinds of problems. And so we talk, all right, so some of your remaining objectives for this module include interpreting diagrams, to follow the sequence of computing actions, and then to complete your related assignments and solutions. So what does that mean in practical terms? You're going to want to spend some time in the addendum. And you're going to want to be able to look at some of the diagrams some of the links and diagrams and know what they are when you see them. So you are going to want to spend some time in the websites and then review the related concepts. So I think we've shown some of this before. We talked about, didn't we talk about vacuum tubes at one point? And transistors, right? I am going to add a couple of symbols to, or maybe a link. I found a TikTok video that's actually pretty concise and very quick. When you're looking at this symbol, what it means and how that works. So in the world of electronics, we use different schematic symbols to represent the related functions for logic gates, right? So as we're building logic gates with physical materials to create those digital components, this is a common schematic representation of something called a resistor. Has anyone ever heard of the term resistor?
Yeah,
Okay. So
it helps with the voltage, right?
well, yes. So what do you suppose would happen if a very powerful resistor was active when electricity was trying to flow? Would it allow the electricity to flow, or would the resistor halt the flow of electricity? In terms of the simple logic of its name, if a resistor was active in a very powerful way, would electricity be allowed to flow unimpeded?
No.
No, it wouldn't. Exactly right. So if electricity cannot flow, what's the Boolean value of that?
0.
It's a 0, right? We've already said that when electricity flows, it's a 1, and when electricity cannot flow, it's a 0. And so what you have here is a resistor that can what? You can activate a resistor, or you can deactivate a resistor. And if you turn off if you basically deactivate a resistor, the electricity flows, and when the resistor, now that's an oversimplification, but the basic concept there is that resistors have important functions that relate to the flow of electricity. Let's leave it at that. When we're building AND gates, remember that we're dealing with, and OR gates, we're dealing with serial versus parallel, remember? Does everybody remember what the little hump means? Are these wires connected or not?
No, it's not.
They are not connected. What about these two wires? Are they connected? Yes or no?
Yeah.
Yeah, they are. That's a splice. Very good. Okay. A NOT gate, right? So you have voltage that's coming in, you have a resistor. You want to be able to identify the schematic elements in each diagram, and you want to be able to interpret them. So you want to understand this represents a NOT. This represents an AND, an OR, an AND. At a basic level, you want to memorize these diagrams. You want to understand, right? Now, that I'll tell you what, we'll just put the TikTok link in there and let you watch it. It's actually again, a pretty efficient thing. Which logic gates are in here?
And
Ands. Yes. And if this is the voltage coming in, then what is this on the other end? Does anyone know? So let's think about the basic flow of electricity. If I have a supply of electricity that's fed into a wire, if you have a complete circuit, what do you have to have on the other end for that circuit to be closed?
A grounding unit.
A ground. You have to have a ground. Very good. In order for the circuit to close and to loop properly, you have to have a ground. If you don't have a ground, then electrons are going to get stuck. They're going to start to flow, but they don't really have anywhere to go. The thing to remember is that the biggest battery in the world is the Earth. But unfortunately, on YouTube, you'll see common examples of con artists who are trying to tell people that you can get free electricity if you just buy their gadget, and it's baloney, right? So in any case, the thing we want you to be able to do is to identify specific symbols. So everybody understands VCC, that's the voltage and current that's fed in. So if I'm looking at this right here, all right, everybody sees these are connectors, right?
yeah,
Okay, and that is a semiconductor, right? It's made out of silicon. And then there are gates that are built into this thing, and we know those are ands. So where does the electricity enter in on this chip, and where does it leave after it's done doing the job? Would anyone care to
Well,
guess?
I think it leaves on this on the right side where it has that ground symbol,
Yeah, right here. Yes,
and I guess
that's ground. That is correct.
well, I'm not entirely sure where it enters. I guess from the top where it has like that little semicircle.
This thing right here.
Yeah.
So where it says VCC,
Oh, I was
that's
looking
like
below that. Okay.
that's like the beginning of that's the electricity coming in, right? So that's the beginning of the source. And then you have these other connectors. Because of the way they're connected, this creates multiple ands. And then on the other end is out, right? Out to ground. So if you don't have out to ground, it doesn't work, basically. Yes, question.
yeah. The semicircle that he was speaking of, does that have any significance?
That's a great question. And hang on just a moment. Oh yeah, we have. So this usually helps in terms of orientation. You know that electronic devices are usually assembled robotically, right? I mean, originally they were assembled by hand, but a lot of factories have robots, right?
Right.
Okay. And if you have a unique, I want to use the term key. If you have a key here, basically that removes all doubt how that chip is implemented with the rest of the circuits. So when you have an integrated circuit, it's not typically the only thing that's in that device. And you'll have other chips and other transistors and other stuff. So the trick is to know exactly how to orient and insert the component into the interface where the connectors can do their magic. if you have it reversed, that can cause serious problems. So to answer your question, let me see here. There was another picture of a CPU we saw on the screen just a moment ago. Is it in here? I think it was in here in the other.
The following program.
No. I was just looking at it. Let's do this. So you were asking about the notch, yeah?
Yeah.
And if we look at the socket, so the socket is the place on the motherboard where the thing goes in. And this isn't as obvious. Let me look at a Pentium, Intel Pentium CPU. There we go. Okay, does everybody see how there's an offset here? There's one corner where there are pins that aren't there.
Yeah, I see.
Okay. So if you look at this, and there's actually a dot on here now. So you see the dot, right? When you're putting it in the socket, you have to put it in the socket the right way. And if you don't, you can take this and it can be turned so that the dot is over here, or over here, or over there. And the problem is that all of these connectors would be out of alignment, right? And actually the CPU wouldn't be able to do its job and it wouldn't function properly. Because there's so much input output on a modern CPU, you have to have a way of guaranteeing the orientation when they're mated with the connectors on the motherboard. So sometimes when you, all right, so this is for an Intel Pentium 4 and when you look at the socket, sometimes the socket doesn't give you a specific indication of where this thing goes. So what you have to do is understand how the orientation is supposed to work. That's where that comes into play. So to answer your question, the reason there's a unique indentation has more to do with how it's plugged in so that it's plugged in right. Have you ever noticed on a electric cord how one of the blades on the electric cord is wider than the other one?
Yeah.
Same kind of thing. So that was a good question, and I'm glad you asked it. Any other questions about this particular topic? So remember, on Wednesday, we do not have class, but go ahead and finish and submit the simple assignment for today in module 4, right? We want you to get on your own computer and have a look at the way that RAM address ranges are set up and used when the digital components are prepared for use with applications. The operating system has this preliminary step that it takes. It uses a special class of software called a device driver to build out this virtual representation of the actual physical device in memory. And just do that on your own system and submit that. Any questions before we clear today?
No, sir.
All right. Thanks for joining us. Enjoy the holiday on Wednesday, and we'll see you on Friday.
Professor, could I speak to you afterwards?
Yes. Hang on.